It's a great honor to be here, especially introduced by Dr. Wang. Just so you know, he was my advisor when I was in Iowa State. So the topic today is eco-efficient SCC with low binder content recycled concrete aggregate. So I do want to point out that I have two parts of work that I present here today. They're pretty brief, not a very large scope of work. But first part was actually done when I was in Texas State, and the second part, the main part, is what I did in Nebraska. So the outline of the presentation, so the first part, as I say, that one was only that bullet point SCC with RCA. That just the work I did when I was in Texas State, that was 10 plus years ago, with self-consolidating concrete made with incorporation of recycled concrete aggregate with both coarse and fine recycled aggregate. But then the second part is Eco-SCC with RCA, the work I've done in Nebraska. Besides incorporation recycled aggregate, we also try to play with the binder content just to see if we can reduce the binder content to further reduce the carbon footprint. So the work that will mostly be presented and from that project. So as what you see over here, besides a brief introduction be materials, results from fresh concrete property, hardened concrete property, impact of the playing with the binder content, impact of the RCA content, and then we have something related to particle packing, and then the global warming potential, so toward the end. So, okay, the first part is SCC with recycled concrete aggregate. So there are a lot of work done with SCC. There are also quite a lot of work done with SCC with recycled concrete aggregate. I do also want to point out that because I'm the last one in these two sessions, so you don't see any picture of those slump flow, J-ring, and so on. So assuming you know what it is, if not, ask. So the material we use for this part of research, so you see that I have the gradation over here with the coarse aggregate, fine aggregate, and then this remind me that at that point that when I was in Texas, they used manufactured sand and also mixed with about 10% of silica sand. That's their natural fine aggregate. You see that our recycled fine aggregate is this gradation, and then recycled coarse aggregate is this one. They're a little bit coarser than both the natural coarse and fine, but we did not really specifically look into gradation. We just use whatever we have. But we did separate coarse and fine so that we can play with them. Mixture design-wise, you see three BC tables. We have three series. Series A, Series B, these are the two series with recycled fine aggregate to partially or completely replace natural fine aggregate. That's what you see over here. RCFA fine recycled concrete aggregate, you can see from 0 all the way to 100% compared to natural fine aggregate, and the other component pretty much remain the same. That's Series A. Series B is very similar to this. The difference is Series A with fairly high binder content. So that's the SI unit, that's the empirical unit. Total binder content, I don't have the total binder content, but this one is higher than Series B, which is slightly lower. So 700, this one is a series without fly ash, just a cement. Binder content 700 remain the same. 700 PCF or 415 kilogram per cubic meter. So, and again, same thing, use recycled fine aggregate to partially and then completely replace natural fine aggregate. Series C was a group with recycled coarse aggregate. So for this one, we basically use recycled coarse aggregate to partially and then completely replace natural coarse aggregate. So, and this is a BC slide. So with the results, basically, you don't need to look into other numbers. Basically, green means good, meaning green means meet the criteria, red means below the, or does not satisfy the criteria. So basically, the key information, key takeaway from this is, yes, we can make that work. So when you replace natural coarse or natural fine aggregate, you can still achieve the SCC property with the design we have. You can see that most of the mix actually have largely green. There are few of the mixes, especially with the higher replacement level. We have something with like L-box blocking ratio, V-funnel. These are likely because the shape of the aggregate could lead into that. But mostly we see most of the mixes actually meet the criteria. The other thing is mechanic property. Compressive strength, you can see over there with the RC, the first series A, actually they're very much comparable until you hit that 100% replacement. But then with the other series B, you can see a slight drop, especially with 50, 70, 100%, and coarse aggregate replacement, they're little drop but quite comparable. One interesting we see, but overall they're all pretty high. You see that everyone's higher than 35 megapascal, which has no idea how much PSI that is, but fairly high, much higher than the required strength. But the interesting we notice is, especially on the Series A mixes, likely because high amount of cement. If you look at the shrinkage, again, I apologize that the font is pretty small over here. Comparing to the reference mix, which is that one over there, all the mixes show a lower amount of shrinkage, which was a surprise. But keep in mind, these are recycled fine aggregate mix, which recycled fine aggregate has higher absorption capacity. If you're familiar with the concept of internal curing, they actually could very much be that internal curing potentially contribute to the low amount of shrinkage. So that's fairly clear in the Series A mix. Series B, we actually see some mix also have lower shrinkage. So, but not as clear, that likely because maybe not that high amount of cement for these two benefit to show up. So that's basically the part that I say with SCC with recycled concrete aggregate with both coarse and fine. So consider that as more or less the appetizer. Now we get into the main dish, which is Eco-SCC with RCA. So as I mentioned that with what we did, and for that part I just presented, we know we can make it happen. With recycled concrete aggregate, we can make SCC work. But now we want to look into, can we further reduce the carbon footprint? Can we reduce the binder content? That's the main thing we want to look at. So what we did is basically try to come up with this eco-efficient SCC with because a couple of things. One is material cost, especially SCC tend to have higher binder content. And if you can drive the cost down with reduced cement content, that will definitely make it more attractive. The other thing is that we want to look at if there's any technical benefit, particular things like, do we have low amount of shrinkage, and can we have other properties that's comparable or even better? So that's basically the idea behind this. So before we get into the mixture design, this is a concept behind this. So, and just as I mentioned earlier, the first part was what I did in Texas State, and this part was at Nebraska, and this part is actually, Dr. Wong know that very well. That's actually from my PhD dissertation in Iowa State. I basically complete my 3 parts here in United States. So the idea behind this, just very quick in case you're wondering what exactly is this, the fresh concrete behavior is largely depend on the amount of paste you have inside. So basically, in general, we know that, well, the higher amount of cement content, the higher the workability. But on the other hand, when you look at the paste, most of the cement paste is used to fill the space among the aggregate particles. That amount will not contribute to workability, if that makes sense. So because the first thing you want to do if you mix concrete, you want to make sure you have enough paste so that you don't have voids. Then you start to add more. Then basically you can start to separate the aggregate so that you have workability. So look at the color over here. The light blue color are those that you need to fill the voids among aggregate particles. But the part really contribute to your workability are the green part, which basically are the part that separate aggregate with aggregate particles, meaning that part will actually help you to flow. So with that being said, conventional concrete versus SCC tend to have more paste because you need further separation to get a higher flow. But if you can somehow figure out a way to reduce the blue color, meaning the color, the void content you need, the cement paste to fill the voids, you can reduce the total cement paste content. So basically, that's comparison you see over here that with better particle packing, you can reduce the blue color, you can get comparable green color. That's a goal behind this. So getting into the aggregate, so we use natural coarse aggregate, natural fine aggregate. In this case, different from the previous one that we actually just combine the recycled coarse and fine basically as it is. So that's why you see that we don't have a separate recycled coarse aggregate, recycled fine aggregate. They're just recycled aggregate. The gradation is in between. So the aggregate properties over here, specific gravity absorption, fineness models, you can see that this actually recycled aggregate is really coarse, fairly close to the natural coarse aggregate. So mixture design, we have two groups, two series. So the first series is basically without recycled aggregate, but we just want to play with binder content. So what you see over here is that these mix are already kind of optimized the gradation. I don't have the detail over there, but with that, we want to see that will this allow us to reduce the binder content. That's what you see over here. The binder content, this one I have the number over here. So 650, 600, 550 to 500 pound per cubic yard. If it's SI unit, 360, 385, drop to below, a little bit below 300 kilogram per cubic meter. So, and again, as I mentioned, for this one, we actually don't have the recycled aggregate. So we just want to see how it behaves. What you see over here is flow-wise, they are very much actually so for the first three mixes with standard binder content and keep dropping, the first three actually you don't see much drop. So basically, this tells you that yes, you have enough cement paste for this. Then when you have this one, the slump flow and J-ring flow, both of them drop more compared to the other three. So, and there are other information over here, VSI, compressive strength over here. The research was mostly focused on fresh concrete, so they don't have that much of mechanic property besides compressive strength. But what you see over here is with the P1, P2, P3, P4, basically with the reduction of the cement content, P1, P2, P3 works pretty well. P4 is the one have some issues, including the flow as well as VSI. So in case of wondering why when you have a lower flow, you have a VSI 1, if you remember what Dr. Marcos presented early, VSI 1 meaning that you have some stability issue. So basically this is a mix we actually, because we reduce quite a lot of cement paste, we actually have to add high amount of super plasticizer that actually lead to some stability issue. So overall, we feel comfortable with P1, P2, P3, and then, but P4 is the one we said that's too much. So with that being said, now that P3 become our reference mix, and we went to the a series of 3 mixes with the incorporation of recycled aggregate. So basically, this is like we already reduced the binder content. So from the reference mix, we actually reduced 100 pounds per cubic yard of cement content and can make SCC. And I want to see that if we can make SCC with recycled concrete aggregate with reduced cement content. So the mixture design is based on the P3 mix. Now you have the increase of the recycled aggregate basically to replace, I remember that's only to replace natural coarse aggregate, because as I mentioned, the aggregate, even those have the fine component, but they're fairly close to the coarse aggregate, so we decide just for the sake of easiness, and there's another benefit I'll show you a little bit, that we actually just replace natural coarse aggregate. So the results you see over here with the incorporation of the recycled aggregate, actually the flow dropped a little bit, but still they're fairly comparable. They're still kind of within the SCC range. What you see over there, like this R1, R2, R3, that R2 get 24-inch of flow, R3 is 22-inch, is not as flowable, but still, if you remember, Dr. Marcus presented earlier, that's still in the kind of mid-range of SCC flow. The J-ring flow, VSI, they're all stable. Compressive strengths, again, as I mentioned, they are actually quite comparable. Actually, the R2 mix is actually higher than the reference mix with only natural aggregate. So the other thing I want to show you is we do not have the measurement of rheology, but for those of you familiar with the concept that the slump flow is largely related to yield stress, that T50, I don't think I mentioned that, T50 is when you do slump flow, after you pour the slump corn, you want to measure how fast it reached that 50 centimeter range. That basically gives indication of viscosity. So what I want to show you is that you see that I put the 2 groups together, meaning the 2 different papers, 2 different research. What you see over here is the Eco-SCC mix with a lower slump flow. That's an indication of that the mix kind of have higher with yield stress. So, but you think about this, these are the mixes actually with lower binder content, higher aggregate content. So that's kind of correlate to the initial mixture design. So to kind of, we're getting close. I want to show you how the binder content and the RCA impact the strength of these. So basically, as I mentioned earlier, you do see a reduction with the reduce of the cement content, but they are still high enough for most of the needs. And then same thing with recycled aggregate. Even with that 50% replacement, you actually have higher strength. So the question is why and how we make this work. So some of the mix actually with recycled aggregate, you have better flow, some with higher strength. Remember I mentioned earlier on about particle packing. So basically, for those of you who are not familiar with this equation, the modified Anderson model, that's usually people use to do particle packing. So that equation basically gives you the minimum particle size, maximum particle size at Q is a factor depending on what kind of concrete. So again, as I say, some of you might not be familiar with that, but I assume most of you know 0.45 power curve. That's when you do aggregate gradation. Do I? Yes, no? So 0.45, that 0.45 is a Q. So actually we use that. Just a lot of people don't know that 0.45 actually, the underlying equation is this. So nevertheless, so we use this basically to look at our gradation. So if you look at these, based on the parameter we choose a Q, the power number of 0.27, which is most people use in that range for SCC. So when you look at that, the one with the natural aggregate only, or the dash line one, is the ideal gradation. Basically, the concept is if it's close to that one, you get better gradation, better particle packing that lead into better workability and can allow you to reduce the binder content. So this one, the brown one, is the natural aggregate. And then the green one and then the blue one, R2, R1, they are the two with recycled aggregate. Especially that R2 one, you see that they're fit compared to the other, they're very close to the ideal gradation. So that kind of explains why you have better flow and better strength, because you have better particle packing. So we did not intentionally design our aggregate gradation based on this, but we actually do it afterwards. So just so you know, again, this is not a very intensive project, so we have very limited amount of mixes over here. With that, I do want to show you this. Again, particle packing, play with gradation. This is the most important concept if you want to play with the binder content. So 818, ACI 302, these are kind of gradation band people use. What you see over here is kind of give you a general sense that from the black line, which is natural aggregate, to 50% replacement of recycled aggregate, 100%, we actually happen to have better gradation. Use this traditional gradation band. And this is 818, ACI 302, and then torrential curve, which is more designed for pavement concrete. But nevertheless, you see a better gradation, which is kind of similar to what you see in that theoretical curve. And the other thing, just since we're talking about Eco-SCC, that E, I kind of see it here, that again, this just, it's not intentionally. I don't want you to take away that you have to have an E shape of particle distribution to get there, but I want to just say that yes, we can make it eco-friendly. So again, don't take it from me that that gradation band need to be the E shape. It's not actually the case. So there's something similar to what Gilson did early on related to the environmental impact. So we basically look at the greenhouse potential for each of the component. The biggest one is always cement. Just keep that in mind. So what you see over here, that's equivalent, well, 1 kilogram of CO2 equivalent 0.81 kilogram of CO2. And the others are much lower. So with that being said, if you see, we put a mixture design together. We have the Eco-SCC, which is here, comparing to the other mixes than the normal SCC. Those are with those SCC with recycled concrete. That's the first part I present. Those are with higher binder content. Again, the main contributor is the blue one. That's cement. So if you can reduce that one, the GWP will drop significantly. So I want to show you that how big an impact this could be. So you actually drop like close to 50% with a reduced cement content. No, not 50, because that's not zero. About 30%, I would say. Yeah. Anyway, so with that, just to wrap it up, the developed Eco-SCC mix included study, including the two with recycled aggregate. They present good workability, passing flow, that means flow, passing ability, stability, and well-satisfied SCC requirement. The result demonstrate that yes, you can make Eco-SCC with reduced cement content and with recycled concrete aggregate. The CO2 equivalent, as I mentioned earlier, can be reduced by up to 30% with this Eco-SCC mix. But there are a lot of work need to be done associated with this to make it more practical or more often used. So I do have one additional slide with final remarks. So look at how we can reduce the carbon footprint of concrete, particularly SCC, because SCC, one of the things people always look at, you have high binder content. So these are the three things that you can do. Decrease the binder content, use more aggregate, but these two actually connect to each other. The other is use recycled aggregate. So these are what you can do. So on the other hand, I do want to add one more thing is that the other piece of SCC is they are usually considered more used in precast, partially because of high binder content, high cost. But if you can reduce, like in our case, Eco-SCC has a binder content fairly comparable to normal concrete. I mean, it could have potential for us to use in ready-mix concrete. Again, a lot of people hesitate on that, but that's a separate part, like quality control, consistency, and how tiny that window you have. But what I want to show you that, yes, it's feasible, but there's still a lot of work need to be done. So with that, I'll be happy to take a couple of questions.